So now we'll look at the other derivative, which is partial derivative of f with respect to y at the point a, b, with respect to the second variable. So the notation is a little subscript of y is right here, representing taking derivative with respect to the second variable y. Okay, so this is obtained by keeping x fixed, meaning x as a constant, x equals to a, and finding the ordinary derivative at b, which is y equals to b, as a function of g, capital G of y, meaning we replace x by the constant a and keeping y as a variable. Again, we look at the limit, so we keep a as a constant, we vary b. So this is partial derivative of the function f of xy with respect to the variable y. So in a previous example, we'll talk about that. The heat index as a function, heat index I as a function of temperature and the relative humidity, H. So when the temperature is at 96 degrees and the humidity at 70%, so it varies both ways. So we fix one, go to the other one. So the derivative at the function at 96 degrees and 70% humidity with respect to the temperature, the heat index changes to 3.75, meaning for every degree of temperature change, the heat index changed by 3.75. Similarly, the partial derivative with respect to humidity, the second variable H, and the answer is 0.9, which is mean for every percent of the humidity change, the heat index changed by 0.9. So if you now let the point A, B, all right, vary in equation 2 and 3 in the previous equation, and f sub x and f sub y become a function of a two variable, okay? So this is called partial derivative. So even though it's partial derivative, we take a derivative with respect to x, which means x vary. However, we'll fix y as a constant, treat y as a constant. Similarly, if we could take derivative with respect to y, then we're going to vary y. However, we're going to treat x as constant. All right, that's how we deal with the partial derivative. So first of all, let's talk about all the different notation we can have. Obviously, you have seen the subscript of f sub x, meaning partial derivative with respect to first variable. But we're also doing one, meaning the first variable, or the differential operator with respect to the first variable. We also use a notation called, instead of df dx, that's for a single variable. So now we'll use the word, instead of using d, we use del, D-E-L, del f del x. So when you see the del meaning partial derivative already, you already automatically assume f is multivariable. So here are del f del x can be interpreted as a ratio of differential. It's not. It just simply differentiate the function f with respect to the variable x. So let's see. So this, we write it out xy, that's an abbreviation. That's equivalent to del f del x. There's write it out the function f of x and y. Also, because z equal to f of x, we can replace f by z. Similarly, instead of using x as the first variable, we can use a differential operator, or we can with respect to first variable, or differential operator with respect to the x variable. All right, so y is the same here. So to compute partial derivatives, all we have to do is remember from equation 1 that the partial derivative with respect to x is just an ordinary differential derivative treating y's fixed, I would just say y as a constant. So we'll do the same thing as ordinary derivative, meaning just with one variable. It's the following rule. To find the partial derivative of f with respect to x, we regard y as a constant. And we differentiate this with respect to x. Similarly, to find a partial derivative of the function y with respect to y, we regard x as a constant. Therefore, we differentiate this function with respect to y, treating x as a constant. So here is an example here. All right, you have a functions f x y equals to x cubed plus x squared y cubed minus 2y squared. Find the partial derivative with respect to x at 2, 1 and with respect to y at the point 2, 1. So the first one, we're going to find a partial derivative with respect to x. We're going to holding y as a constant. So the derivative of x cubed is 3x squared. Derivative of x squared y cubed, so treating y as a constant, so leave it alone. So it's the derivative of x squared is what, just 2x. Okay? Please do not apply implicit differentiation and product rule here. Okay? And then finally, derivative of negative 2y squared, which is a constant, so it just becomes 0. And then you plug in 2, 1, x, replace x with 2, y with 1, that answer is 16. Now, we're going to find a partial derivative with respect to y. Okay, so do that again. This time, we're treating x as a constant. So the derivative of x cubed, since x is constant, so it becomes 0, it's gone. And derivative of x squared y cubed, remember, we're treating x squared as constant, so the derivative of y cubed, you get 3y squared, and x squared remains as a constant. Finally, derivative of minus 2y squared, which is derivative with respect to y, is a 4y. And you plug in 2, 1. So the answer is 8. So in general, they are not the same.